Hi ladies and gentlemen, we're going to be talking about covalent bonds, and this is going to go along with 8.3 in your textbook. Also, it's going to have a little bit of 8.5 in your textbook as well, so I recommend that you read both of those sections to pick up any last little bits that may be missed on this video. But we're going to be talking about covalent bonds today. And essentially what a covalent bond is, as we know, is an atom that shares electrons to fulfill the octet rule. Mostly they're going to be looking for 8 electrons, although the covalent bonding in hydrogen is only going to have 2 electrons like helium. We could draw Lewis structures and using dots to represent our valence electrons, and just as a reminder, and I think we already know this from regular chem, is that valence electrons are typically equal to whatever group number that atom is in. So coming down here is I'm going to draw a couple Lewis dot structures for each of the following. We'll start off with hydrogen, and hydrogen is in column 1A. It does have 1 valence electron. Now we start with my valence electrons right up there. Oh, what are we doing here? Sorry about that. 1 valence electron right up at the top, just represented by a dot just like that. Do carbon next. Carbon has 4 valence electrons. It's in column number 4. So I typically on my valence electrons will start right at the top at, like, we'll say 12 o'clock if we're looking at a clock. So I put 1 there, 1 there, 1 there, and 1 there, and just go around that way. That way it sets up easily for bonding that we're going to do later on. And then the Lewis dot structure for fluorine here, I'm going to draw it out here, just make it a little bit bigger. Here's fluorine. I'm going to have 7 valence electrons as fluorine is a halogen in column 7A. So there's 4, 5, 6, and there's 7. So that would be the Lewis dot structure for fluorine just by itself. Now we can also draw Lewis dot structures for compounds. And then compounds, one of the things that we want to make sure that we do is we want to make sure that we have completed an octet. We have 8 valence electrons around everybody, with the exception of hydrogen, which is okay with 2. And we're going to talk more about these rules very soon, but let's talk real quickly about methane here, which is CH4. And typically what happens is whoever's listed first, carbon is listed first, that's going to be our central atom. That rule does not always apply, but for the most part it usually does. So, and this is going to be an exception in the next charge. So let's take a look. We have carbon here. We're going to draw that in as the central atom. We're going to put 4 valence electrons around the carbon just like that. We're going to go back over here and we have 4 hydrogens. I'm going to draw a hydrogen here, 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 and here. So we have 4 hydrogens there. Each one of those has 1 valence electron as well. And then basically we're just going to connect the dots. And it doesn't necessarily look as good as it should, but we get the idea done. Now what we're going to do next is we want to double check to make sure everybody's got an octet. This hydrogen here has an octet. It has 2 valence electrons that are being shared, so it's okay with that. Let's say this carbon would have each one of these single bonds represents 2 valence electrons, and so carbon has 2, 4, 6, and 8 there. So it has an octet, so everybody's good to go there. Okay, let's take a look at over here. We have water as H2O. This is one of the exceptions where it doesn't really the first atom is not the central atom. So oxygen is actually the central atom in this case, and water, as we know. And so we're going to do 1, 2, 3, 4, 5, 6 valence electrons. Each hydrogen has 1. And so that's going to form a single bond there, and it's going to form a single bond there. And then we call these, obviously these are called single bonds, but we're going to call these here unshared pairs of electrons. So water has 2 unshared pairs of electrons that are not being involved in bonding that do influence shape of the water molecule. That we'll be talking about that later on in the next chapter. The last one we're going to do is ammonia, and if you want to try this one by yourself and pause the video, that would be a good idea to do right now, and then we'll come back to it. Okay, so now we're going to do ammonia. Central atom is their nitrogen with 1, 2, 3, 4, 5 valence electrons. Hydrogen on each one of those unshared pairs of electrons, just like that. And we could say that nitrogen does have 3 total single covalent bonds plus an unshared pair of electrons on the top that's going to influence the shape of nitrogen. Okay, now we're going to scroll down here a little bit, and we're going to get into multiple bonds. And so I'm going to erase some things here a little bit. Looks like things kind of scroll down on me. Let's get rid of some of this stuff. You can always pause this video if you need to go back and see any of that stuff. So let's talk about multiple bonds. And we have two diatomic compounds plus one just regular old compound. And so for oxygen in a diatomic molecule and multiple bonds, we're going to have each oxygen having 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And so if we're going to go ahead and single bond this oxygen just like this, what happens is this oxygen still does not have an octet. We can look here, and there's only 2, 4, 6, 7 valence electrons there, and that's not completing our octet. And so what we're going to want to do is we want to complete our octet on both these oxygens. So let's take this electron here and this electron here, and let's create a double bond just like that. And then we can get rid of these guys here, get rid of that, get rid of that. And that's actually what the diatomic oxygen molecule looks like. You have double bonds with two unshared pairs of electrons on each oxygen. And we'll talk about how these electrons are all going to organize themselves a little bit later. The next one we're going to do, let's take a look at nitrogen here. Nitrogen, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And so we're going to single bond between here and here. And this guy still doesn't have an octet, so if we're looking at this nitrogen here, it has 2, 4, 5, 6 valence electrons, and that is not octet. We want to get to 8, and so let's see what we can do here. We're going to take maybe this one here and that one there, and make a double bond. Recheck. Still does not have an octet. Take that one there and that one there, and we're going to triple bond. So it looks like nitrogen is going to form a triple bond. And actually, the way this guy organizes itself, let me get rid of these here and here and here, is it's actually going to have these unshared pairs of electrons get as far away from each other as possible. And so they're going to organize themselves like that. And so this guy's not going to erase on me. There it goes. Maybe not. There we go. So that's what our diatomic nitrogen is going to look like. For carbon dioxide, this is one where we have our carbon as our central atom, and so we're going to put carbon there, and we're going to put an oxygen on each side. 1, 2, 3, 4 carbons in group 4. We're going to do oxygen. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I lied, there's 6, right? There we go, 6. Okay, so oxygen's in column 6. So we're going to single bond here. And we can single bond there. And if we look at anybody, nobody has an octet here. We have oxygen on the left-hand side with 2, 4, 6, 7 valence electrons, not happening yet. So let's go ahead and take one of these electrons here and here and make a double bond there. And take one of those electrons there and make a double bond there. And now everybody's got an octet, and so everything's good, and that's what our carbon dioxide molecule looks like. Next thing we're going to talk about here is bond length. And bond length is defined as the distance from the nuclei to the nuclei of a different bonded atom. So in looking at some bond length measurements involving nitrogen, if you were to have a nitrogen-nitrogen single bond, it would be at 147 angstroms, double bond 124, single bond, or I'm sorry, triple bond, so the triple bond trying to be illustrated there, it's 110. So the takeaway on bond length is that single bonds tend to be longer than double bonds, and double bonds tend to be longer than triple bonds, which are, of course, the shortest. And so there's our takeaway there, is triple bonds are short, single bonds are long. And so here's a sample question that says, comment on the bond lengths in HCN. So HCN is one of these molecules we're going to have to draw. Hydrogen is not the central atom. This guy is given as, this is the way HCN actually looks. So you have a single hydrogen, and then a carbon, and then a nitrogen. And so let's work this guy here. So we have 1 valence electron for hydrogen, 4 valence electrons for carbon, and we're going to have 5 valence electrons for this nitrogen. So let's go ahead and single bond there. Go ahead and single bond there. And it looks like hydrogen has satisfied its octet, so it's okay. I don't want to do that. That illustrates something else. Let me get rid of that real quick here. But carbon and nitrogen have not satisfied their octet. So let me cross out, and put a bond there, cross out there, and put a bond there. So it turns out what HCN actually is, and this is really sloppy, it looks like this. And so if we wanted to comment on this, we would say that the hydrogen carbon bond is the longest, where the carbon triple bond nitrogen is the shortest. And that's how we could comment on that. Okay. Now, if we're getting into drawing Lewis structures that are a little bit more complicated, and that's where 8.5 comes in your textbook, I highly recommend you read that, that we have a couple rules that go along in place. And it looks like my computer renumbered some of these rules because it felt like it started with number 10, and that's not where we wanted to start. We wanted to start with number 1. And so the first thing you do if you have a more complex compound is you want to count the total number of valence electrons on everybody, and we'll do that here in a minute. And then we already talked about in number 2, what you're going to want to do is you're going to, whoever's listed first is typically the central atom, although that's not always the case. HCN is a great example where it's not, or water. You want to go ahead and single bond everybody, make that rule number 3. Number 4 is you're going to single bond, you're going to complete octets by moving electrons around or even creating multiple bonds. We've been doing that. And on number 5 is if you have any leftover electrons on the central atom, just go ahead and place them there. Or if you have any leftover electrons at all, place them on the central atom. This may violate the octet rule, but that's okay, and we'll talk about how we can violate the octet rule and when we can violate it. And we'll be doing that more in the coming days. So let's give you an example here of what we're talking about. So PCl3, a little bit more complicated atom, but not by much. So what I'm going to do here is I'm going to calculate my total number of valence electrons first. Chlorine has 7 valence electrons. We have 3 chlorines, so that's going to be a total of 21 valence electrons. Phosphorus is in group 5, so phosphorus is going to have 5 valence electrons, and so that's going to give us 26 total valence electrons to work with. So I'm going to put central phosphorus, chlorine, chlorine, and chlorine. I'm going to single bond everybody. And in that case, I've just used up 2, 4, 6. So now I'm down to 20 electrons to deal with, and I'm going to go ahead and place them all around. So I want 20. So there's 2, there's 4, there's 6, 8, 10, 12, 14, 16, 18. And everybody's got an octet, and we're satisfied, and that's what a PCl3 molecule looks like, and we'll talk about the shape of this guy in another chapter. So we can use that to calculate, do that. Let's look at this next one. We have CH2Cl2, and so what this guy does is carbon's got 4 valence electrons, hydrogen's got 2 more, it's going to give us a total of 6, and then 2 chlorines is 7, 7, 14. So we're going to add 14 to this. So it looks like we have 20 valence electrons to play with. This guy is going to, carbon tends to be the central atom of most molecules. So we're going to do carbon here with a hydrogen coming off here and here. And then we'll put a chlorine coming off here and here. And so we have 20 valence electrons to play with. So we're going to go 2, 4, 6, 8, just like that. Hydrogen isn't going to take any more. So we're just going to go for the chlorine. So we want to use up, we just used up 8, so we have 12 more valence electrons to work with. 2, 4, 6. I'm going to make sure that's 2 right there. And 8, 10, 12. And that's what that molecule is going to look like. And let's do our last one here. And if you want to pause the video again, you can pause it and do this yourself and then check this out afterwards. But we have C2H4. Each carbon is going to be 4. And then we have 4 more, so we're going to have a total of 12 valence electrons here. Carbon and carbon are going to be in the center, and we're going to do hydrogen here, and then we'll do hydrogen here and hydrogen here. Single bond everybody, 2, 4, 6, 8, 10. Okay, so we have 10 there, but we still have 2 more valence electrons to work with. And when we're looking at the central carbons, they only have 6 valence electrons now. So I'm going to go ahead and put a double bond there. And that is how we do C2H4. So there will be a worksheet that goes along with tonight's homework, and hope you have a nice evening.